Hello there, I'm Dr. Vivian Lowe, and you're on vlmd Rounds, a podcast on medical science and tools to optimize your health. Those of you who've been following this podcast, welcome back. And again, I'd just like to encourage you to go to my website, vlmd.com, vyvyanelohmd.com. And under events, you can look up the live Q&A sessions that I generally have. And these are about once a month. You can just kind of sign on and ask me questions, suggest topics, and just, chat with me for a little bit. So I hope to see some of you there at the upcoming live stream events. Also, please subscribe to the newsletter where I'll give you a heads up on some upcoming episodes and maybe some projects that I'm working on. And also feel free, as usual, to make your requests for different topics. Some of you have made requests and my request list is growing quite long, but I'm keeping tabs of all your requests, so no fear, I will get to those topics. Now, in the last few weeks, we've been talking about the cells of the immune system. So we started with the innate cells, and then last time we went into the B cells. This week, I'm going to go into the T lymphocytes. So let's go. All right, now when we talk about the T cells, if you remember, when we were discussing the B cells, we talked about the B cell receptor. So let's start with the T cell receptor. Now, the T cell receptor is made up of protein chains, just like the B cell receptor. If you remember again, the B cell receptors, you have the light chain, the heavy chains, right? Here we have alpha, beta, or gamma, delta protein chains, okay? So you're going to have the alpha chain and beta chain, or you're going to have gamma and delta chains, okay? One or the other pair is what you have. And 95% of T cells actually have the alpha beta chains, and these will also express other molecules that we'll talk about later on, the CD4 and CD8 molecules. So the alpha beta of the T cell receptor, they can recognize MHC molecules and whatever's presented in those molecules. If you recall from the episode on the innate immune system, we talked a little bit about those MHC molecules, and I likened them to social media platforms, right? So we have MHC1 molecules, MHC2 molecules, which the MHC stands for major histocompatibility complex, okay? So the MHC1 molecules, you can post whatever's going on inside the cell, inside your own house, all right? The MHC2 platform is used to post whatever's going on in your environment, whatever information you gather from the environment. You took pictures of what your neighbors are doing, you can post that on MHC2. So we have these MHC molecules and the postings, and the alpha beta chains, these recognize the MHC molecules and the posts that are presented on them, okay? And just to, be complete, I just want to point out we also have a very small subset of T cells that are called natural killer T cells, or NKT cells. About 1% of your T cells are of this subset. And your other T cells are going to recognize protein fragments, right? That's what your MHC molecules and whatever they post, those are protein fragments. However, these NKT cells, they actually recognize lipids. So that's one of the main differences between them and other T cells. All right, So your T cell receptor, we have the alpha beta, or we have the gamma delta chains. Mostly, let's just focus on alpha beta. That's the most common, right? But they actually, those chains don't have very long cytosolic components. So this means that they're not really going to be useful for signaling. So just like the B cell receptors needed accessory proteins like the Ig alpha and the Ig beta to help with signaling, here the T cell receptors need also, a protein complex. Now we have actually 4 chains here that make up the complex, and these are gamma, delta, epsilon, and zeta. I want to point out that the gamma and delta here are different from the gamma and delta of the T cell receptor. They're different. They're not the same, okay, which is why it's kind of confusing sometimes. But the gamma delta here, together with epsilon and zeta, make up a protein complex, and we'll just refer to that complex from now on as CD3 complex, okay? Just easier that way. So this whole complex is the signaling part of the T cell receptor, the CD3 complex. Now, when the T cell receptor recognizes its cognate antigen, it binds to it, and we also need to have the same thing that we saw with the B cell receptor, that clustering effect, right? Where you bind to different epitopes on the antigen, you bind those epitopes and you bring all the T cell receptors together and you cluster them. So that's really important. And when you cluster them together like that, then basically the CD3 can, that protein complex CD3 that's involved with signaling, that can recruit and activate certain enzymes that will now send a signal to the nucleus, right? And have the nucleus express specific genes that would be part of that activation process, okay? So we need that CD3 part of this complex to actually send the message to the nucleus, express genes that are associated with that inflammatory response. In addition, these T cells require co-receptors, okay? And these are the CD4 and CD8 molecules that we talked about, right? So when you have the T cell receptor recognize its cognate antigen, it also needs to have one of these co-receptors that will be involved in the interaction. And these co-receptors are important because they dictate the function of those T cells. The CD4 co-receptor is associated with MHC2 molecules. So it recognizes and binds to MHC2 molecules. Remember, this is the platform that allows you to post about what's going on in your environment. The CD8 molecules are going to be associated with MHC1 molecules. So they actually bind to the platform that allows you to post about what's going on inside the cell, okay? Now, when you have a T cell that has a CD4 co-receptor, then that T cell is a helper T cell, okay? That becomes its function. It becomes a helper T cell. When it has CD8, then that becomes a killer T cell or a cytotoxic T cell, okay? So remember that those CD4, CD8 co-receptors are really important because they're going to dictate the function of the T cells. Now, after binding, right, we have the T cell receptor binding to the cognate antigen and also the co-receptors, whether it's CD4 or CD8. We still need something else because that interaction, that reaction is not going to be very strong. So we're going to have to amplify this signal. And in order to do that, we're going to need co-stimulation to amplify this T cell receptor binding effect. And this is through those antigen presenting cells. If you remember again, we talked about antigen presentation in the innate immune system, right? And really the professional antigen presenting cell of your body is the dendritic cell. And this cell is able to present antigens to the adaptive cells. Okay, so in this case, we have an antigen presenting cell, a dendritic cell, and it has also co-stimulatory molecules on its surface, different types of co-stimulatory molecules. The most famous or well-known of these would be B7 protein. And this B7 protein expressed on the dendritic cell is able to fit with a receptor called CD28 on the T cells. All right, so B7 on the antigen presenting cell, or the APC, is going to fit into the receptor CD28 that you find on T cells, and this allows now co-stimulation to occur. So let's just look at the T helper cells and their activation, okay? So again, we start with the dendritic cell, and these dendritic cells, they have adhesion molecules all over them that help them stick to T cells, right? And then, because they're T helper cells, remember, so they have CD4 molecules. So the CD4 molecules, when it finds the MHC2 molecules, it's going to attach there, okay? So we have the antigen presenting cell gets sticky, and then these T cells are likely to bind to them, and then CD4 finds the MHC2 molecules and binds or associates with it to strengthen the interaction between the antigen presenting cell and the T helper cell. Now, the T cell also has CD40 ligand, 40, CD40 ligand, and this binds to, guess what, CD40, right? The corresponding CD40 on the antigen presenting cell, the dendritic cell in this case. When that happens, we're going to upregulate this B7 protein, right? And also the MHC molecules there. And so now we're going to allow co-stimulation to be upregulated there as well. Okay, so this is what happens with the T helper cells. And now these T cells are going to proliferate, and they're stimulated by a cytokine called interleukin-2. These T cells initially, when they are immature, they are able to make interleukin-2, but they don't really have receptors on their own surface for interleukin-2. But once they have been activated, now they're going to start expressing interleukin-2 receptors on the surface, and that in itself is going to stimulate the proliferation of those cells. So it's kind of a nice little feedback loop there. Okay, so that was the activation of the helper T cells, CD4 T helper cells. Let's now look at the killer T cells. Now remember, they have CD8. So again, they go around and they have to be able to recognize antigen that's presented on MHC1 platform, okay? And then CD8 will also bind to the MHC1 to strengthen that interaction. But we also need one other thing. We need an interaction from the T helper cell. And what happens is, remember we had the T helper cells, once they are activated, then they can bind to dendritic cells. And with that binding, they're going to have that dendritic cell express cytokines and also MHC1 molecules, okay? They're going to help that dendritic cell specifically express more of the MHC1 molecules now, because that's what the killer T cells recognize, right? And this will help activate those killer T cells. So for activation of killer T cells, remember, we need MHC1, we need CD8, we need also this T helper activation of those dendritic cells so that we upregulate cytokines and MHC1 to help, activate the killer T cells, right? That's why they're called helper T cells, because they help do all kinds of things. Now that you have activated T cells and the killer cells, killer T cells, right? They are now functional. And when they are functional, they can do their job, and we now call them effector cells, okay? Because they can go about now and do their business. So what would be their business? Let's look at the functions of the different types of T cells. Essentially, when we talk about the T helper cells, we're talking about making cytokines. That's what they do. They're going to make these signaling cytokines. All right, so they're essentially almost factories for making cytokines. When we talk about T helper cells, you'll often read about these different subsets, and they are Th1 or T helper 1, Th2 and Th17 subsets, and they, classically are described, these subsets, as having specific cytokines that they produce depending on what subset they are. Okay, that's just how they're described. In reality, it's not quite like that. It's not so clear cut. So if you remember when we talked about macrophages and we talked about M1 and M2 polarization of macrophages, M1 being more inflammatory and M2 being anti-inflammatory, I said that's just one way for us to kind of think about them. But in real life, you're never going to have M1, M2. You're going to have this range and a spectrum of inflammatory and anti-inflammatory effects depending on the context. Okay, so it's never clear, black and white. And it's the same with these TH subsets. So even though we describe them as Th1, Th2, Th17, and each subset, classically secretes different types of cytokines, in real life, it's more of a mix, and you're going to have these T cells, these T helper cells, secrete a range of cytokines, and it's going to be very context dependent as well. Okay, so how do we kind of determine what cytokines are secreted? This is very dependent on the antigen presenting cell, that dendritic cell. The dendritic cell, remember, is at the scene of the infection, and it picks up all kinds of cues and information from the scene, right? The macrophages as well, right? So they're constantly sampling the environment there. Also, those dendritic cells are going to know what tissue has been infected, right? So if they're in the skin, they will record, the environmental factors in the skin and so forth, right? They'll record information about the pathogen that has invaded the skin. And they bring all this back to the lymph node, and they present this now to the T cells. So let's say there was a bacterial infection, and this dendritic cell now goes to the lymph node, and there it's going to express interleukin 12. Okay. Once it secretes interleukin 12, then that's basically an instruction for those TH helper cells to become classical Th1 cells, right? And their cytokine profile will then be TNF, and interferon gamma, and interleukin 2. Okay, those are the classical cytokines associated with a Th1 profile, right? Now, let's say instead that you had a helminth infection, so worms, okay, parasites, worms. Then that dendritic cell is going to elicit a Th2 cytokine profile, right? And those would be interleukin 4, interleukin 5, and interleukin 13, right? So when you have helminth infections, parasitic infections, we're going to instruct those helper cells to be that Th2 profile and secrete that subset, more or less, of cytokines. Now, what about if you have an infection, let's say, at a mucosal surface, so maybe in the intestines, right? Then those dendritic cells in that area, they're going to express TGF beta, they're going to express interleukin 6, interleukin 23, and this is going to elicit a Th17 cytokine profile, all right? So now we have Th17 T cells, and we'll have interleukin 17 and interleukin 23 and interleukin 21 that are secreted by those cells. And as I said, that's a generalization, but in reality, there's a mix and match and there's a range of cytokines that will be secreted. In addition, we also have Th0 cells, and these cells are really not committed to being a specific subset of T cells. And the beauty of it is they only make that commitment once they arrive at the site of infection. So if they arrive at the site of infection and they realize, oh, okay, I need to be a Th17 cell, then they start expressing the cytokines of the Th17 profile, all right? So those would be the Th0 cells. So now that we've talked about the helper T cells, let's move on to the cytotoxic T cells, or the killer T cells. And remember, these have CD8 and they recognize MHC1 molecules. So the way they kill is they produce a protein called perforin. And this perforin punches a hole in the invader's cell membrane. Okay, remember I mentioned in, I think, the last episode that your immune cells really like punching holes in things. So here we have the killer T cell with perforin punching a hole in the pathogen's cell membrane, and then it's going to like deliver all kinds of granzymes with cytotoxic chemicals in them onto the surface of the pathogen. All right, now that cell thinks, ooh, there's a hole in my membrane. I better go try and fix that. And in the process of trying to fix that damaged part of the membrane, it's going to inadvertently bring in the perforin and the granzyme. And once it brings that into its own cytoplasm, that stuff is really toxic to the cell, and it's going to cause that cell to self-destruct. So that's one way those T cells are going to kill the pathogen, via perforin and granzymes. A second way is via the Fas ligand. We discussed this, I believe, in the last episode as well. So the CD8 T cells have Fas, F-A-S ligand on them, which will bind to Fas that is on the target cell. Okay, and once they bind, it's going to have that target cell self-destruct, okay, undergo apoptosis. And of course, the CD8 T cells also secrete cytokines such as interferon gamma, and that will help upregulate more MHC1 molecules, which it can recognize on the cells that are nearby. All right, so we've discussed the functions briefly of the different T cells. One thing now we must talk about is how these T cells come about, because they are born in the bone marrow just like the B cells, but they have to undergo specific testing, and this occurs in an organ called the thymus, Thymus, the thymus, which is like right here underneath your sternum, right at the bottom of your neck, underneath, behind the sternum, in front of your heart. It's a tiny little organ. And in fact, T cells are called T cells because that T stands for thymus. And, you know, we often say that the T cells are educated or tested in the thymus. All right, so we have these immature T cells first enter the thymus via the bloodstream, right? And, you know, they're coming from the bone marrow, they get into the bloodstream and they go to the thymus and enter there. And at first, they're going to be at the periphery of the thymus, okay, and we call that the cortex. That's the outer part of the thymus gland, okay. So they're in the cortex and they start to proliferate and they rearrange their gene segments, you know, that little shuffling process to make that specific alpha beta chain or gamma delta. All right, we're just going to use alpha beta at this point, right? They'll make the alpha beta chains of the T cell receptor. And then they're going to express a few of these T cell receptors on the surface. And this is complete with that CD3 signaling part, right? So that whole unit, now we have a few of them scattered on the surface of these immature T cells. In addition, they are going to express both CD4 molecules and CD8 molecules. At this stage, they have both CD4 and CD8, and so we call them double positive cells. Okay, this is not going to be forever, but at this point in time, they are double positive. I like to think of these T cells, immature T cells entering the thymus as gladiators almost. Okay, sometimes that's how I visualize them. They come in and they're gladiators, or selected to be gladiators. And when they come in, they don't have a lot of that FAS antigen. Remember, when FAS binds to FAS ligand, right? Then we have apoptosis. So they don't have a lot of FAS on them, which is good because we don't want them to be vulnerable to apoptosis. And in addition, they have a protein called BCL2, okay? And BCL2 is sort of like a shield because it's protective against apoptosis. So these immature T cells enter the thymus, and at first they have, you know, very little FAS and they have a lot of this BCL2. But once we actually have made the T cell receptor with the CD3 complex and we have a few of these expressed on the cell surface, now something changes. What we're going to do is we're going to take these gladiators to be, and we're going to actually increase a lot of expression of the FAS antigen on them. And in addition, we're going to strip away that BCL2 protein. Remember, that was protective. So now these poor gladiators, they're stripped of their defense, BCL2, and we've actually upregulated FAS antigen on them. And so now they're very vulnerable to, you know, apoptosis, to dying. And it's in this state that they are going to be tested. And this test is called a test for MHC restriction, and sometimes it's also known as positive selection. Okay, the cells that are going to test our gladiators will be the cortical thymic epithelial cells, small c, and then capital T, capital E, capital C, the CTECs, the cortical thymic epithelial cells. And they are going to be testing our new gladiators. And what they want to know is whether these T cells can recognize the MHC platforms. So remember, we have MHC1 and MHC2 and whatever's posted on those platforms, right? And the CTECs want to know, all right, you new gladiators, can you pick out the platforms? Can you recognize MHC1, MHC2, and the postings associated with them? Okay, and if the answer is yes, and those T cells can recognize MHC molecules and the associated postings in them, then okay, we passed that first test. All right, so those are victorious. They go on to live for another day. Okay, and the rest die. Remember, they have plenty of that fast antigen and they don't have much of the BCL2. So if they don't pass the test, it's the end for them. Okay, we get rid of them because what's the point of having these T cells that can't recognize the MHC posting platforms? You know, because that's how they're going to recognize antigen. They have to do it through those MHC platforms. And if you can't even recognize the platforms, what use do we have for you? Let's just get rid of you, okay? Because you're costing us too much energy to have around and you're not very functional, all right? So the CTECs, now classically, remember I told you the MHC1 molecules post whatever's going on inside the cell, and MHC2 can post whatever's outside in the environment, right? But with the CTECs, they have a way of posting whatever is going on inside the cell on both MHC1 and MHC2. Okay, they can do it on both platforms, whatever's going on inside the cell. So it's not the usual scenario, but the main question they're trying to answer is, can those immature cells recognize an MHC1 or an MHC2? You got to recognize one of them, okay? Otherwise, we get rid of you. So that's the first test. Now, right after this, right, we're going to also do something else. Remember, they were double positive. They had both CD8 and CD4. Now we got to get rid of one of those co-receptors, okay? We have to get rid of them. So if that T cell had recognized an MHC1 molecule, right? If it recognized the MHC1 platform, then CD8 is going to bind and associate with that MHC1 molecule, right? And when that happens, we're going to downregulate and get rid of CD4, okay? So we've committed to CD8. If we bind to the MHC2 platform, then CD4 is going to bind to those MHC2 molecules, and now we're going to get rid of CD8. Okay, either way, we're going to get rid of one of them. So you're either going to now be a CD8 T cell or a CD4 T cell, right? And when we get to that point where they are now single positive, right? They started with both, and now you have one or the other, so now they're single positive, then they start to express a chemokine called CCR7, and this will attract them to a place that has the corresponding CCR7 ligand, which happens to be the center part of the thymus. We call that part the medulla of the thymus, medulla. All right, so now these cells that pass that first test, right? So these gladiators now have to go on to the second test, and that happens in the medulla region of the thymus. That first test, remember, we called it MHC restriction or positive selection. This second test is called negative selection. And what happens here is they're going to be tested now by the medullary thymic epithelial cells. Okay, that first test was by the cortical thymic epithelial cells, now the medullary thymic epithelial cells, or the MTECs. Okay, and what the MTECs are going to do is they are going to display self-antigen. Okay, when I say self-antigen, it's like, okay, part of myself, part of the cell itself. Okay, I'm going to display some, protein fragments that come from myself on either MHC1 or MHC2. Technically, you're only supposed to post what's outside the cell on MHC2, but again, these MTECs can get away with it. So they're posting their self-antigens on 1 and 2. And what they want to know is, would that T cell now recognize the self-antigen that comes from the cell itself? Okay, and if the answer is yes, we got to get rid of those T cells. Okay, why? Because if you're going to be a T cell that recognizes your own self-antigen, right, then we're going to have an autoimmune effect and you're going to destroy your own cells. Not a good thing. So we don't want those around. Okay, so that's the test that's happening. They're going to present their own proteins and say, can you recognize this? And if you do, then you're too dangerous and you're going to destroy us all. So we have to get rid of you. Now, in addition, we have specific proteins that are only expressed in different tissue. So for example, we have special proteins that you only see in the liver. And you have special proteins that you only see in the kidneys or in the lungs, right? So we have to make sure that those T cells are not going to recognize those tissue-specific proteins from your own body, right? And for that, we have AIRE, which is a transcription factor, and it's capital AIRE, all in caps. Okay, AIRE, and that's the autoimmune regulator. It's a transcription factor, and what it can do is it can have that cell, the MTECs, express many different tissue-specific antigens. It can express proteins that come from, like I said, the liver, or your lungs or your heart. Okay, so it's going to do that and present it on the MHC platform and see what happens. Make sure that we don't allow the T cells that recognize those antigens to live. We got to get rid of them, right? In addition, we have thymic dendritic cells, and these came from the bone marrow, but then they kind of lived in the thymus. And these MTECs can also pass on antigens to these specific thymic dendritic cells, and these dendritic cells are going to present antigens to those T cells, again looking to see if they're going to recognize their own proteins. And if they do, you don't want those around, right? So if you recognize your own self-antigens, then we have to get rid of you. So, you can see that we have to make sure that we have the right T cells that we're going to allow loose in the body. So you have about 60 million T cells enter the thymus every day, and you're only going to have about 2 million appropriate T cells allowed to leave the thymus alive, okay? Because a lot of them, if they can't recognize the MHC molecules in that first test, we get rid of. And if they recognize self-antigen, we get rid of those as well. In addition, we have a subset of T cells that we call the natural Tregs, okay, or regulatory T cells. And these are actually CD4 T cells. And here, they're tested. Now, when we talk about the testing in the medullary region with the self-antigens, Really, it's a matter of how well those T cells recognize self-antigen. If they very strongly recognize the self-antigen, those are the ones we get rid of. We don't want those around. If there's a very weak recognition, okay, we'll let those live. Okay, those that have intermediate affinity, intermediate levels of recognition, those are going to be the regulatory T cells, the natural regulatory T cells, and that would be about 5% of your CD4 T cells. All of these regulatory or Tregs are going to express FOXP3 gene, okay? And what they do is they're going to, when they go to the lymph nodes, they're going to suppress any other T cells that may recognize self-antigen that somehow escaped the thymic testing, okay? So if they go to the lymph node and there was a T cell that had escaped the thymic testing somehow, got out there and can recognize self-antigen very strongly, then these regulatory T cells, they recognize the self-antigen and then, with intermediate affinity, and they're going to be activated. And when they do that, they're going to decrease the expression of the co-stimulatory molecules on your antigen presenting cell, right? So remember, we needed co-stimulation with those antigen presenting cells, but the Tregs are going to prevent that, and as a result, we're not going to have activation of those T cells that are going to recognize the self-antigen, right? So those are the natural Treg cells. And just to be complete, we also have inducible Tregs. Those are slightly different in the sense that they also express FOXP3 genes. However, what they do is they're going to suppress the overreaction to foreign antigen. So you've been attacked by a bacteria, right? And we recognize that antigen and we're going all out to kill it. But these inducible Tregs are going to make sure that we don't become overreactive against that antigen, because that's going to cause destruction in your own body as well, and you're going to have that immune system go out of control, right? So it's there to regulate and decrease co-stimulation of those by those antigen presenting cells in that scenario, okay, in the context of invasion by a foreign pathogen. But when we talk about the self-antigens, right, that's going to be with the natural Treg cells, and they decrease co-stimulation by APCs so that we don't activate those T cells that are going to recognize self-antigen. So when you have that T cell and it does recognize the self-antigen, but it's not getting that co-stimulation from the APC cells, then they are going to undergo anergy. A-N-E-R-G-Y, anergy. And this means they're basically non-functional, okay? So they're not going to work, and over time they'll just die off. That's what it means when we talk about anergy. Just to finish off, I know we're mostly talking about T cells here, but this is also true of B cells. We don't want your B cells to recognize self-antigen as well. So the B cells, they are born and they are, educated in the bone marrow. They just, everything done in the bone marrow. So if we have a B cell that recognizes self-antigen, it's first of all given a chance. Basically we say, okay, B cell, go back and rearrange those gene segments and come up with something else, okay? Because this is not going to work, because this recognizes, this BCR, this B cell receptor recognizes self-antigen. So go reshuffle those gene segments and come up with something else. And about a quarter of those B cells that recognize the self-antigens, they'll try to reshuffle. But even then, many of them will still not pass the test. And in essence, only 10% of all of the B cells that are made in your bone marrow actually pass this tolerance test, okay? So once we have any B cells that escape the bone marrow that can recognize self-antigen, then the issue with them is they're just not going to be helped. They're not going to be stimulated by the T helper cells, and they in turn become energized, and so they'll eventually die off, right? They're also non-functional, okay? So that's the whole concept of energy in these immune cells. All right, so I think we can now go into our wrap up. Let's see, we started off by looking at the T cell receptor, and those are formed of those alpha beta chains or gamma delta, one or the other pair, okay? And then we mix and match gene segments and we come up with a specific alpha beta pair or a gamma delta pair. And 95%, most of them are going to be alpha beta, right? So we have now the T cell receptor, and that can recognize the MHC platforms and whatever is on them. Now, we also have another part that is necessary, the signaling part. And so we have a protein complex in the cytosolic region that is called CD3, all right? And that's the part, once the TCR recognizes the cognate antigen, then we can signal through the CD3 protein to the nucleus to express certain genes, right? And also now at this point, when the TCRs are clustered and that signaling goes to the nucleus, we can see that they begin to be activated. We have CD4 and CD8 molecules. They are co-receptors and very important in antigen recognition. The CD4 molecules are associated with class 2 MHC molecules. CD8 would be associated with class 1 MHC molecules. And if you have a T cell with CD4, that's a T helper cell. If you have a T cell with CD8, that's a killer T cell, right? So we have to have the TCRs and the CD4 or 8 molecules bind, but we also need co-stimulation to amplify this binding effect. And most commonly, we have B7 protein that's expressed on antigen-presenting cells that can now fit into the CD28 receptor on the T cells. And once we have that happen, we can start to activate those T cells, right? And we have different functions with the different types of T cells. The T helper cells crank out cytokines. We have subsets that we recognize. So we have Th1, Th2, and Th17 subsets. You'll read about them. And each subset classically expresses a specific cytokine profile depending on how they're stimulated by the dendritic cell, because the dendritic cell goes to the site of infection, gathers information. Based on what it finds, it's going to send out cytokine signals and molecules, and this will now incite those T helper cells to become Th1, Th2, or Th17 helper cells and express the cytokine profiles associated with those subsets. And that's, of course, just what it looks like in the textbooks. In real life, it's not so clear-cut. It's a lot messier, and you have a range of different cytokines that can be expressed, again, depending on the context. And in addition, we have the Th0 helper cells, and these don't really express any cytokines until they get to the site of infection, take a look around, and in the context of what's going on at that site, they will now express the most useful, helpful cytokine profile. So they'll, go towards a Th1 or Th2 or Th17 profile. Now, the killer T cells do exactly what their name describes. They basically kill. And the way they can do this is through perforin and granzyme, which when taken into the cell causes the cell to self-destruct. They also have Fas ligand, FAS, and that binds to Fas on the pathogen, let's say, and this will cause the pathogen to self-destruct. And in addition, they secrete interferon gamma, and this will upregulate more MHC1 molecules so that they can recognize those pathogens more quickly. Now, in terms of the T cells, they're named after the thymus where they are trained. And we have the T cells born in the bone marrow, travel in the bloodstream, get into the thymus, and they go first to the outer region of the thymus that is called the cortex of the thymus, CORTEX. And there, they shuffle their gene segments and they make specific TCRs, alpha beta chains that are specific TCRs. And they have the CD3 complex attached, so they can also signal. And at the time, they also express CD4 and CD8, so they are double positive. Now, they are somewhat protected in the beginning from apoptosis because they don't have a lot of fast antigen and they have a lot of BCL2 protein, which protects them from apoptosis. Then they, just before they're tested, we're going to strip them of the protective BCL2, downregulate those protective proteins, and we're going to upregulate the fast antigen, and then off they go for the MHC restriction test, also known as the positive selection test. And this is done by the corticothymic epithelial cells, or the CTECs, and essentially they're going to start presenting posts or proteins on their MHC platforms. And the key question here is, do these cells recognize the MHC platforms? Okay, they've got to distinguish those platforms from just other molecules that are expressed on the CTECs. Okay, so if they don't recognize those MHC molecules, then we just get rid of those T cells because they're useless at this point, right? If they do recognize the MHC molecules, then what we're going to do is, if they recognize, for example, MHC1 molecules, then CD8 is going to bind to the MHC1 molecule as well. And at the same time, we're going to get rid of CD4 and vice versa. If it's MHC2 that the T cell recognizes, then CD4 is going to bind to MHC2 and we're going to get rid of CD8. So now instead of being double positive, they are single positive. They're either going to have CD8 or CD4. And if you are a CD4 cell, then you're going to eventually be a T helper cell. CD8s are eventually going to be the killer T cells, but there's one more test, right? So now they migrate from the cortex of the thymus and they're going to go to the central region called the medulla. And in the medulla, they're going to be tested by the medullary thymic epithelial cells, or the MTECs. And the big question here is, okay, are these T cells safe? Right? Are they going to harm our own bodies? And the way they would do that is if they recognize self-antigen. So if they recognize, antigen that comes from your own body, then you're going to have autoimmunity. That's not a good thing, right? You don't want those T cells attacking your own body. So we need to make sure that they're the right T cells. So the MHC molecules are now going to express self-antigens on those platforms, on both MHC1 and MHC2, and test those T cells, now the single positive T cells, right? In addition, we're also going to express these proteins that are made by the air transcription factor, the autoimmune regulator, right? We're going to make and express these proteins that come from specific tissues, such as liver, such as lungs, such as heart, okay? And we're going to put them on those MHC platforms because we don't want your T cells to recognize your own heart proteins or your own kidney proteins, right? These are only expressed in those tissues. So we got to test them in the thymus, right? So we're going to express these via the MHC platforms, or these MTECs are going to hand over some of these antigens to the thymic dendritic cells, and those APCs are going to present to the T cells. So obviously, if you recognize self-antigen strongly, we're going to get rid of you. We don't need you around because you will cause destruction to the body itself. If you recognize your self-antigens weakly, we'll spare you, we'll let you live. If you have an intermediate affinity, okay, for those self-antigens, then you could become a natural T regulatory cell or natural Treg. And these will express FOXP3 genes, and what they do is they're really not going to allow activation of any T cells that can recognize self-antigen well that have escaped the thymus testing. Okay, so if somehow they escape that testing and they get out into the body and they can recognize self-antigen very strongly, right? Those Tregs in that area, they recognize the self-antigen with intermediate affinity. And once they do that, they're really going to decrease co-stimulatory molecules on the antigen-presenting cell so that we can't actually co-stimulate those T cells that recognize self-antigen. And those cells now undergo anergy. So they recognize the antigen, but they're not co-stimulated. So they become non-functional. And that's what anergy means. And then eventually they die off. And a similar thing actually happens with B cells, right? And that is a protective effect. Again, the last thing we want is your own immune cells attacking your body. Okay, so that was a very quick overview of the T lymphocytes. And there's just so much more detail that I left out, as usual, just because, you know, it's really hard to go into the nitty-gritty. But I think it's a good place to start. So now we've looked at the innate cells, we've looked at the B cells, we've looked at the T cells, and we have a general idea of how all these different cells work, and more importantly, also how they work together, right? We often will talk about the innate immune system and the adaptive immune system as if they were separate, and they are in a way, but there's so much collaboration and interaction between the two systems. And really all those cells make up, you know, the whole of your immune system. Okay, so that's it for this episode. I did get through the main cells that we wanted to talk about in the immune system. And this will help us a lot when we go into different topics that address autoimmunity and inflammation. Okay, so signing out now from vlmd Rounds, I'm Dr. Vivian Lowe, and I sing the body electric. See you next time. Bye.